Welcome to this comprehensive Calculus 2 lesson. Today, we're going to embark on a journey through some of the most powerful and essential topics in calculus. By the end of this video, you will be able to master advanced integration techniques, understand and evaluate improper integrals, analyze the convergence of sequences and series, work with power and Taylor series, and apply integration to find arc length and volumes. We'll start by building on your knowledge of basic integration and move into more complex methods. Then, we'll explore the fascinating world of infinite processes with improper integrals, sequences, and series. Finally, we'll see how integration can be used to solve real-world geometric problems. Let's begin with our first major topic, advanced integration techniques. Our first objective is to master advanced integration techniques. We'll start with a method that's essentially the reverse of the product rule for differentiation. This technique is called integration by parts. The formula for integration by parts is derived directly from the product rule. It states that the integral of u times dv is equal to u times v minus the integral of v times du. Let's write that down. The integral of u dv equals uv minus the integral of v du. The key to using this method is choosing the parts u and dv correctly. A helpful mnemonic for this is LIATE. LIATE stands for logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential functions. You should choose u as the function that appears first in this list. Let's see this in action with an example. Consider the integral of x times e to the x. We want to evaluate the integral of x e to the x dx. Using LIATE, x is an algebraic function and e to the x is an exponential function. Since a comes before e, we choose u equals x. So we set u equals x, which means du is dx. The remaining part, e to the x, dx, must be dv. Integrating dv gives us v equals e to the x. Now we plug these into our formula. The integral becomes u times v, which is x e to the x, minus the integral of v du, which is the integral of e to the x dx. The new integral, the integral of e to the x, is much simpler to solve. The integral of e to the x is just e to the x. So our final answer is x e to the x minus e to the x, plus our constant of integration, c. And that's how integration by parts works. You transform a difficult integral into a simpler one. Next up, we have a set of techniques for integrals involving trigonometric functions. These are called trigonometric integrals. The strategy here depends on the powers of sine and cosine. Let's consider integrals of the form sine to the m of x times cosine to the n of x. We're looking at integrals of sine to the m of x times cosine to the n of x. Case 1. If the power of cosine, n, is odd, we save one cosine factor and use the identity cosine squared of x equals 1 minus sine squared of x. So if n is odd, we save a cosine and use the identity cosine squared equals 1 minus sine squared. Case 2. If the power of sine, m, is odd, we save one sine factor and use the identity sine squared of x equals 1 minus cosine squared of x. If m is odd, we save a sine and use the identity sine squared equals 1 minus cosine squared. Case 3. If both m and n are even, we use the half-angle identities. Sine squared of x equals 1 minus cosine of 2x over 2, and cosine squared of x equals 1 plus cosine of 2x over 2. If both are even, we use the half-angle identities to reduce the powers. Let's try an example. Let's evaluate the integral of sine cubed of x times cosine squared of x. We want to find the integral of sine cubed of x times cosine squared of x dx. Here, the power of sine, m, is 3, which is odd, so we'll use case 2. We save one sine factor and rewrite the rest. We can rewrite sine cubed as sine squared times sine. So the integral is sine squared of x times cosine squared of x times sine of x dx. Now, we use the identity sine squared of x equals 1 minus cosine squared of x. Substituting this in, we get the integral of 1 minus cosine squared of x times cosine squared of x times sine of x dx. This integral is now perfectly set up for a u substitution. Let u equal cosine of x. If u equals cosine of x, then du equals negative sine of x dx. This is exactly what we have in our integral. Substituting u and du into the integral gives us a much simpler form. The integral becomes the integral of 1 minus u squared times negative du. Distributing the negative sign, we get the integral of u to the fourth minus u squared du. This is a simple power rule integral. Integrating gives us u to the fifth over 5 minus u cubed over 3 plus c. Finally, we substitute back u equals cosine of x to get our answer. The final answer is cosine to the fifth of x over 5 minus cosine cubed of x over 3 plus c. By following these cases, you can tackle a wide variety of trigonometric integrals. Sometimes, an integral contains a square root of a quadratic expression. For these, we use a technique called trigonometric substitution. This is trigonometric substitution. The idea is to substitute x with a trigonometric function to eliminate the square root. There are three main cases. Case 1. If you see the form the square root of a squared minus x squared, you substitute x equals a sine of theta. This simplifies to a cosine of theta. Case 2. If you see the form the square root of a squared plus x squared, you substitute x equals a tangent of theta. This simplifies to a secant of theta. Case 3. If you see the form the square root of x squared minus a squared, you substitute x equals a secant of theta. This simplifies to a tangent of theta. Let's work through an example. Let's evaluate the integral of 1 over x squared times the square root of 9 minus x squared. We want to find the integral of 1 over x squared times the square root of 9 minus x squared dx. This matches case 1. With a squared equals 9, so a equals 3. We make the substitution x equals 3 sine of theta. We set x equals 3 sine of theta. This means dx is 3 cosine of theta d theta. The square root term becomes the square root of 9 minus 9 sine squared of theta, which simplifies to 3 cosine of theta. Now we substitute everything into the integral. The integral becomes the integral of 1 over 3 sine of theta squared times 3 cosine of theta, all times 3 cosine of theta d theta. Notice that the 3 cosine of theta terms cancel out, simplifying the integral significantly. We are left with the integral of 1 over 9 sine squared of theta, which is 1/9, times the integral of cosecant squared of theta d theta. The integral of cosecant squared is a standard integral. The integral is negative 1/9 cotangent of theta plus c. We're not done yet. Our answer is in terms of theta, but the original problem was in terms of x. We need to substitute back. To do this, we draw a right triangle based on our original substitution, x equals 3 sine of theta. Since sine of theta is x over 3, the opposite side is x, and the hypotenuse is 3. By the Pythagorean theorem, the adjacent side is the square root of 9 minus x squared. Now we can find cotangent of theta from the triangle. Cotangent is adjacent over opposite, which is the square root of 9 minus x squared, all over x. Substituting this back into our answer gives the final result. The final answer is negative 1/9 times the square root of 9 minus x squared, all over x, plus c. Trigonometric substitution is a powerful tool for integrals involving these specific quadratic forms. Our final advanced integration technique is for rational functions, which are fractions where the numerator and denominator are polynomials. This is called partial fraction decomposition. The goal is to break down a complex fraction into a sum of simpler fractions that are easy to integrate. This method only works if the degree of the numerator is less than the degree of the denominator. If it's not, you must first perform polynomial long division. The decomposition depends on the factors of the denominator. Let's look at the cases. Case 1. For each distinct linear factor, ax plus b, in the denominator, you get a term a over ax plus b. Case 2. For each repeated linear factor, ax plus b to the k, you get k terms. a1 over ax plus b, plus a2 over ax plus b squared, and so on, up to ak over ax plus b to the k. Case 3. For each distinct irreducible quadratic factor, ax squared plus bx plus c, you get a term, ax plus b over ax squared plus bx plus c. Let's try an example. Let's evaluate the integral of x plus 7 over x squared plus x minus 2. We want to find the integral of x plus 7 over x squared plus x minus 2 dx. First, we factor the denominator. X squared plus x minus 2 factors into x plus 2 times x minus 1, so we have the integral of x plus 7 over x plus 2x mun dx. Now we set up the partial fraction decomposition. Since we have two distinct linear factors, we use case 1. We write x plus 7 over x plus 2 x mun equals a over x plus 2 plus b over x1. To find a and b, we multiply both sides by the common denominator, x plus 2, x1. This gives us x plus 7 equals a times x mod 1 plus b times x plus 2. A quick way to solve for a and b is to choose convenient values for x. Let's try x equals 1. If x equals 1, the a term disappears. We get 1 plus 7 equals b times 1 plus 2, which is 8 equals 3b. So b equals 8/3. Now let's try x equals negative 2. If x equals negative 2, the b term disappears. We get negative 2 plus 7 equals a times negative 2 minus 1, which is 5, equals negative 3a. So a equals negative 5/3. Now we can rewrite our original integral. The integral of x plus 7 over x plus 2 x1 is equal to the integral of negative 5/3 over x plus 2 plus 8/3 over x1 dx. These are simple logarithmic integrals. The integral is negative 5/3 times the natural log of the absolute value of x plus 2 plus 8/3 times the natural log of the absolute value of x mod 1 plus c. And that completes our tour of advanced integration techniques. You now have a powerful toolkit to tackle a wide range of integrals. Now let's move on to our second major topic, improper integrals. Improper integrals. An integral is called improper if it has an infinite limit of integration, or if the integrand has an infinite discontinuity within the interval of integration. Let's start with the first type, integrals with infinite limits. Type 1, infinite limits. To evaluate an integral from a to infinity of f of x dx, we replace the infinity with a variable, say t, and take the limit as t approaches infinity. So, the integral from a to infinity of f of x dx is defined as the limit as t approaches infinity of the integral from a to t of f of x dx. If this limit exists and is a finite number, we say the integral converges. If the limit is infinite or does not exist, we say the integral diverges. Let's look at an example. Consider the integral from 1 to infinity of 1 over x squared. We want to evaluate the integral from 1 to infinity of 1 over x squared dx. First, we set up the limit. This is the limit as t approaches infinity of the integral from 1 to t of x to the negative 2 dx. Now, we evaluate the definite integral. The integral of x to the negative 2 is negative x to the negative 1, or negative 1 over x. Evaluating from 1 to t gives negative 1 over t minus negative 1 over 1, which is 1 minus 1 over t. Finally, we take the limit. As t approaches infinity, 1 over t approaches 0, so the limit is 1. Since the limit is a finite number, the integral converges to 1. This means the area under the curve y equals 1 over x squared from 1 to infinity is exactly 1 square unit. Now let's look at the second type of improper integral. Type 2, infinite discontinuities. This occurs when the function f of x has a vertical asymptote within the interval of integration. For example, the integral from a to b of f of x dx, where f has a discontinuity at x equals b. To evaluate this, we again use a limit. We replace the point of discontinuity with a variable, say t, and take the limit as t approaches that point. So the integral from a to b of f of x dx is the limit as t approaches b from the left of the integral from a to t of f of x dx. Let's try an example. Let's evaluate the integral from 0 to 1 of 1 over the square root of x. We want to find the integral from 0 to 1 of 1 over the square root of x dx. Notice that at x equals 0, the function 1 over the square root of x is undefined. It has a vertical asymptote there. So this is a type 2 improper integral. We set up the limit, approaching 0 from the right. This is the limit as t approaches 0 from the right of the integral from t to 1 of x to the negative 1/2 dx. Now, we evaluate the definite integral. The integral of x to the negative 1/2 is 2 times x to the 1/2. Evaluating from t to 1 gives 2 minus 2 times the square root of t. Finally, we take the limit. As t approaches 0, the square root of t approaches 0, so the limit is 2. The integral converges to 2. This means the area under the curve y equals 1 over the square root of x from 0 to 1 is exactly 2 square units, even though the function goes to infinity at one end. Understanding improper integrals allows us to calculate areas and volumes over infinite regions or for functions with discontinuities. Let's shift gears now to our third major topic, sequences and series. Sequences and series. A sequence is an ordered list of numbers, like a function whose domain is the set of positive integers. A series is the sum of the terms of a sequence. A sequence is a list, and a series is the sum of that list. The main question we ask about a series is whether it converges or diverges. Does the sum of infinitely many terms approach a finite number, or does it grow without bound? We have several tests to answer this question. Let's start with the ratio test. The ratio test. The ratio test is particularly useful for series involving factorials or exponentials. It states that we should compute the limit of the absolute value of the ratio of the n plus 1 th term to the nth term. We calculate L, which is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. The conclusion depends on the value of L. If L is less than 1, the series converges absolutely. If L is greater than 1, the series diverges. If L equals 1, the test is inconclusive. Let's test the series. The sum from n equals 1 to infinity of n squared over 2 to the n. We want to test the series. The sum from n equals 1 to infinity of n squared over 2 to the n. Here, a sub n is n squared over 2 to the n, so a sub n plus 1 is n plus 1, squared over 2 to the n plus 1. We set up the ratio of a sub n, plus 1 to a sub n. Now we simplify this expression. We can rewrite this as n plus 1 squared over n squared times 2 to the n over 2 to the n plus 1. This simplifies to 1 plus 1 slash n squared all over 2. Now we take the limit as n approaches infinity. The limit as n approaches infinity of 1 plus 1 slash n squared over 2 is 1 squared over 2, which is 1/2. Since L equals 1/2, which is less than 1, the ratio test tells us that the series converges absolutely. The ratio test is a very powerful tool for determining the convergence of many series. Another important test for series is the alternating series test. The alternating series test. This test applies to series whose terms alternate in sign, like 1 minus 1/2 plus 1/3 minus 1/4, and so on. These are called alternating series. An alternating series has the form the sum of negative 1 to the n times b sub n, or negative 1 to the n plus 1 times b sub n, where b sub n is a positive sequence. The alternating series test has two conditions for convergence. First, the sequence b sub n must be decreasing. Second, the limit of b sub n as n approaches infinity must be 0. If both conditions are met, the series converges. Let's test the famous alternating harmonic series. We want to test the series, the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n. In this series, b sub n is 1 over n. Let's check the two conditions. First, is b sub n decreasing? Yes, because 1 over n plus 1 is less than 1 over n. Second, is the limit of b sub n 0? Yes, the limit of 1 over n, as n approaches infinity, is 0. Since both conditions are satisfied, the alternating series test tells us that the series converges. This is a great example of a series that converges conditionally. If we took the absolute value of each term, we would get the harmonic series, which diverges. But because of the alternating signs, the sum converges. Our fourth major topic is power series. Power series. A power series is a series that contains powers of a variable, x. It looks like a polynomial with infinitely many terms. A power series centered at a is the sum from n equals 0 to infinity of c sub n times x minus a to the n. The key question for a power series is, for what values of x does the series converge? The set of all such x values is called the interval of convergence. To find the interval of convergence, we use the ratio test. The result of the ratio test will be an expression involving x. We set this expression less than 1 and solve for x. Let's find the interval of convergence for the series, the sum from n equals 1 to infinity of x to the n over n. We want to find the interval of convergence for the sum from n equals 1 to infinity of x to the n over n. We apply the ratio test. A sub n is x to the n over n, and a sub n plus 1 is x to the n plus 1 over n plus 1. The limit as n approaches infinity of the absolute value of x to the n plus 1 over n plus 1 divided by x to the n over n simplifies to the limit of the absolute value of x times n over n plus 1. As n approaches infinity, n over n plus 1 approaches 1. So the limit L is the absolute value of x. For the series to converge, we need L to be less than 1, so we need the absolute value of x to be less than 1. This means negative 1 is less than x, which is less than 1. This is our preliminary interval of convergence. However, the ratio test is inconclusive at the endpoints x equals 1 and x equals negative 1. We must test them separately. First, let's test x equals 1. The series becomes the sum of 1 over n, which is the harmonic series. We know this series diverges. Next, let's test x equals negative 1. The series becomes the sum of negative 1 to the n over n, which is the alternating harmonic series. We just saw that this series converges by the alternating series test. Since the series converges at x equals negative 1 but diverges at x equals 1, we include negative 1 in our interval but exclude 1. The final interval of convergence is the interval from negative 1 inclusive to 1 exclusive. The radius of convergence is half the length of this interval, which is 1. Finding the interval of convergence is a crucial step in working with power series. Building on power series, we can represent functions as infinite polynomials using Taylor and Maclaurin series. Taylor and Maclaurin series. A Taylor series for a function f of x centered at a is given by this formula. The sum from n equals 0 to infinity of the nth derivative of f evaluated at a divided by n factorial times x minus a to the n. A Maclaurin series is simply a Taylor series centered at a equals 0. The Maclaurin series is the sum from n equals 0 to infinity of the n-th derivative of f evaluated at 0 divided by n factorial times x to the n. Let's find the Maclaurin series for the function f of x equals e to the x. We want to find the Maclaurin series for f of x equals e to the x. We need to find the derivatives of f of x and evaluate them at x equals 0. The first derivative is e to the x, the second is e to the x, and so on. The n-th derivative is always e to the x. Evaluating at 0, we find that the n-th derivative at 0 is always 1. Now we plug this into the Maclaurin series formula. The Maclaurin series for e to the x is the sum from n equals 0 to infinity of 1 over n factorial times x to the n. Let's write out the first few terms. This is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. This series converges for all real numbers x. This means we can approximate the value of e to the x by using a finite number of terms from this series. Taylor and Maclaurin series are incredibly useful for approximating functions, solving differential equations, and evaluating integrals that are otherwise impossible. For our final topic, let's explore some applications of integration to geometry. Applications of integration? First, let's find the arc length of a curve. The arc length L of a smooth curve, y equals f of x from x equals a to x equals b is given by this formula. L equals the integral from a to b of the square root of 1 plus the square of the derivative of f of x dx. Now let's look at volumes of solids of revolution. These are solids formed by rotating a 2D region around an axis. The disk method is used when the solid has no hole. The volume 5 is the integral of pi times the radius squared. The disk method V equals the integral from a to b of pi times the radius squared dx. The washer method is used when the solid has a hole. The volume is the integral of pi times the difference of the outer radius squared and the inner radius squared. The washer method V equals the integral from a to b of pi times outer radius squared minus inner radius squared dx. The shell method is often easier when integrating with respect to the other variable. The volume is the integral of 2 pi times the radius times the height. The shell method V equals the integral from a to b of 2 pi times the radius times the height dx. Let's find the volume of the solid formed by rotating the region bounded by y equals x squared, y equals 0, and x equals 2 about the y-axis. We want to find the volume of the solid formed by rotating the region bounded by y equals x squared, y equals 0, and x equals 2 about the y-axis. Since we are rotating about the y-axis and our function is in terms of x, the shell method is the most straightforward. We'll use the shell method. For a vertical shell, the radius is the distance from the y-axis to the shell, which is x. The height of the shell is the height of the region, which is y equals x squared. The radius is x, and the height is x squared. The region extends from x equals 0 to x equals 2, so our integral is from 0 to 2. The volume is the integral from 0 to 2 of 2 pi times x squared dx. Simplifying the integrand, we get 2 pi times the integral of x cubed dx. This is 2 pi times the integral from 0 to 2 of x cubed dx. Now we evaluate the integral. The integral of x cubed is x to the 4th over 4. Evaluating from 0 to 2 gives 2 to the 4th over 4, which is 16 over 4, or 4. So the volume is 2 pi times 4, which is 8 pi. And there you have it. Integration is not just about finding antiderivatives. It's a powerful tool for solving real-world problems in geometry, physics, and engineering. Let's quickly recap what we've covered today. We've taken a comprehensive tour of Calculus 2. We started with advanced integration techniques, integration by parts, trigonometric integrals, trigonometric substitution, and partial fraction decomposition. We then moved to improper integrals, learning how to handle infinite limits and discontinuities. We explored sequences and series, using tests like the ratio and alternating series tests to determine convergence. We built power series and Taylor series to represent functions as infinite polynomials. And finally, we saw how to apply integration to find arc length and volumes of solids of revolution. You are now equipped with a robust set of tools to tackle more complex problems in calculus. The key to mastering these topics is practice. To help you solidify your understanding, here are a few practice questions. Pause the video, try to solve them on your own, and then resume to see the detailed solutions. Here are your practice questions. Take your time. When you're ready, let's go through the solutions. Let's go over the solutions to the practice questions. Solution 1. Evaluate the integral of x squared times the natural log of x dx. This is an integration by parts problem using LIATE. L, logarithmic, comes before A, algebraic, so we choose u equals ln of x. We set u equals ln of x, so du is 1 over x dx. We set d, v equals x squared dx, so v is x cubed over 3. Applying the formula, we get u times versus minus the integral of v du. This is ln of x times x cubed over 3 minus the integral of x cubed over 3 times 1 over x dx. The new integral simplifies to x squared over 3. The integral is x cubed over 3 times ln of x minus the integral of x squared over 3 dx. Integrating x squared over 3 gives x cubed over 9. The final answer, is x cubed over 3 times ln of x minus x cubed over 9 plus c. Solution 2. Evaluate the integral from 0 to 1 of 1 over the square root of 1 minus x squared dx. This is an improper integral of type 2 because the integrand is undefined at x equals 1. We set up a limit. This is the limit as t approaches 1 from the left of the integral from 0 to t of 1 over the square root of 1 minus x squared dx. The integral of 1 over the square root of 1 minus x squared is a standard integral. The antiderivative is the inverse sine of x. Now we evaluate the definite integral and take the limit. We have the limit as t approaches 1 from the left of the inverse sine of t minus the inverse sine of 0. The inverse sine of 0 is 0. As t approaches 1 from the left, the inverse sine of t approaches the inverse sine of 1. The inverse sine of 1 is pi over 2, so the limit is pi over 2. The integral converges to pi over 2. This result is actually the area of a quarter circle with radius 1. Solution 3. Find the interval of convergence for the series. The sum from n equals 0 to infinity of x minus 3 to the n over n plus 1. We use the ratio test. A sub n is x minus 3 to the n over n plus 1. The limit as n approaches infinity of the absolute value of the ratio simplifies to the limit of the absolute value of x minus 3 times n plus 1 over n plus 2. As n approaches infinity, n plus 1 over n plus 2 approaches 1. So the limit L is the absolute value of x minus 3. For convergence, we need L less than 1, so the absolute value of x minus 3 must be less than 1. This means negative 1 is less than x minus 3, which is less than 1. Adding 3 to all parts, we get 2 is less than x, which is less than 4. This is our preliminary interval. Now we test the endpoints. At x equals 2, the series becomes the sum of negative 1 to the n over n plus 1. This is an alternating series that converges by the alternating series test. At x equals 4, the series becomes the sum of 1 over n plus 1. This is a p-series with p equals 1, which is the harmonic series, and it diverges. So we include x equals 2, but exclude x equals 4. The final interval of convergence is the interval from 2 inclusive to 4 exclusive. The radius of convergence is 1. Congratulations on completing this comprehensive Calculus 2 lesson. We've covered a lot of ground today, from advanced integration to the fascinating world of infinite series and their applications. Remember, the key to success in calculus is consistent practice. Work through more examples, try different types of problems, and don't hesitate to review the concepts. Thank you for watching and keep up the great work.